Hello everybody. So we're going to start with our first lecture on differential equations. So this is the title of the course, Differential Equations. Now, perhaps you have an idea what this means or you don't. One thing you know is you needed calculus in order to enroll in this class, and this is, as you'll see, extremely important because constantly we're going to do integrations. And I use other techniques from calculus, so mostly Calc 2, but there are also some stuff of Calc 1 that we will use once in a while. And I also provided a review sheet for Calc containing the most important formulas that we will be using, so a little review in case you have taken this a bit, it's a while ago that you took this. So I definitely encourage you to look at it before perhaps starting anything else, but also at times that you get a little bit stuck or something, you want to look up something, you can go first to that review sheet because it's made specifically for this course. So it contains like everything that you need to know for this course. So look this first, and if that doesn't solve your problem, then you go back to your calculus books. So what is the link between calculus and differential equations? And before I even say this, why do we do differential equations? Well, perhaps when your instructor talked to you about calculus the first time you took calculus, and they were trying to sell calculus to you and say, oh, calculus is a renovation and innovation from the 17th century that galvanized technological, industrial and scientific advancement, because almost all sciences are based on techniques that are used in calculus. And that is true, that was not a lie, but it is actually not really calculus that we're going to use. It's not through the basic calculus, that was basic calculus that you saw, but it is more actually differential equations that have all these applications to sciences. And when I say sciences, of course, the first thing you think of is physics, but it's also chemistry, economics, many different fields. So what are differential equations then? Well, the word equation means that there's an equal sign somewhere, right? That's one thing. And differential, well, that of course refers to differentiating, taking derivatives. So these are equations involving derivatives. That's perhaps the simplest way of saying what a differential equation is. Now, first of all, equations are in general hard to solve. That might be something that you don't realize because I'm talking now even general equations, algebraic equations and so on. System of equations, for those that have done linear algebra, 2580, you might have seen systems of linear equations. It sounds like they are easy to solve because you have all these methods and you learned how to solve them. But realize that what you saw was about the extent of what we can do. Beyond these equations, more complicated equations are extremely difficult to solve. Even simple equations like this, x to the fifth minus x plus 1 equals 0. We actually cannot write down a solution for this equation in just using the symbols that you learn from algebra. So college algebra, you can write powers and sums and differences and take quotients and take radicals. You cannot express a solution just using that. You can only give a solution in decimal form, basically. And that's a very simple equation. So algebraic equations are already hard to solve. Now, you also know that taking derivatives was not so difficult, but integrating was much more complicated. Again, you might be misled by the fact that all the integrals that you were solving you had methods to solve them, and so it looked like, oh, I can solve everything. No. Again, for instance, this integral ex squared dx we know it exists, by the way. That's the fundamental theorem of calculus, tells you every function has a partial, every continuous function has an antiderivative. This is what an integral is, right? But again, we cannot write it down with the symbols of all the functions that we know from pre-calculus, like exponential, logarithms, sines, cosines. You cannot write down a solution to that. It exists, but you cannot write it down. Okay. So what is this? By the way, what is this means? Let's go quickly see what does this integral mean, right? It means that you're finding a function y such that if it take a derivative, you get ex squared. Remember, that is what an antiderivative is. It's kind of the opposite of a derivative, right? So what function y has derivative equal to that integrand ex squared. So that's one way of writing, an equivalent way of writing this integral as actually an equation. So although an integral doesn't look like an equation, it is actually an equation, and it is exactly what we call a differential equation. A very simple one. We will see much more complicated one. And so the idea here is that we have this y will be, is the dependent variable, we normally call it if we talk about in pre-calculus, but for us it will be a function of x. So it is a particular expression in terms of x. But when I say expression, I have to put this between quotes, because as I said, this guy is an antiderivative of ex squared, so it exists. So in other words, it is a solution, it is the y that we look here, but I cannot write it down as a formula, as an expression of x that doesn't involve an integral sign. Okay? So when I say expression of x, we really have to think, it's really the correct way to say a function of x. It depends on x. For every value of x, you get a y value. Input x, output y. And so we're looking for y's that solve this. But that's not always possible. I just showed you a very simple case. Of course, again, we're going to kind of maneuver around these difficulties, and we will try to get solutions to look at differential equations that we can actually solve. Okay? Although we will talk about how to solve things like this somehow. And perhaps, since it's a bit of an introduction, I'll give you a little hint. This guy, as I said, we cannot integrate, right? This indefinite integral we cannot write down. It's not entirely true if you allow something fancy that you also studied in calculus as a power series. Because with power series, it's really not so hard to write down this antiderivative. But the problem with a power series, it involves infinitely many terms. So it's kind of cheating. You think you have it, but you don't really have it, because you have to write down all these terms that you have you can only really calculate, if you want to calculate these values of this function, only find many of these terms, right? So power series, and we will go all the way towards the end of the course, we will go to these power series and see that we can also solve differential equations using power series. Okay, but for now, let's stick to the more cases that we can solve. Well, of course, that's going to take us many sessions to discuss all different ones, because the thing is also this equation that I wrote on y prime is equal to ex squared is a really simple equation. Let me give an example of a different one. Y prime minus xy is equal to 5. This is also a differential equation. Why? Well, you might say, what is this y double prime? Okay, I know this is double derivative. So first of all, in differential equations, it doesn't have to just be the first derivative. It can be the second and the third and the fourth and any derivative that we want. So differential equations involve equations that involve the function, derivative of the function, but possibly the second derivative and the third and so on, derivative of the function. Okay, so what does this mean? Again, what is the solution to this differential equation? Would be a function, so that if you take the second derivative of the function and subtract x times the function, then you get 5. Okay, now you might say perhaps this doesn't exist. Okay, that's another problem, right? Do these things exist? And if these exist, can we write them down? Okay, so that's a differential equation. I'll say a little what every differential equation therefore is basically. Now how does it, okay, let me give a bit formal definition of what is a differential equation. For us, a differential equation, and a differential equation has something what we call order. So what is the order here? This is order 1, this is order 2, so this is 1. Why? Well, it refers to how many times you take derivative. Here we only take once a derivative, here we took twice a derivative, but what about this one, you think? This is a differential equation because it involves y prime, y double prime, y, and x. So it's an equation involving these quantities, right? What is the order? Well, the highest that we have is 2. So in general, we say order n could be any number, 1, 2, 3, 4, 5, and so on, means that we take the nth derivative of y can be expressed in terms of a function that depends on x, y, y prime, y double prime, all the way up to the n minus 1 derivative. Now this looks like awful, because what is this? Professor, what is this p? Well, that we don't know. It could be it's an expression involving all these quantities. Okay, so like for instance, what would that be here? So in other words, this means that you have to be able to solve for, if it's order 2, you have to be solved for y double, the double derivative, and everything else should now be put on the other side and should not depend anymore on y double prime. But it depends, for instance, as you see here, I should minus sign, right? It depends on the y prime, it depends on y, and it depends on just x. Okay, so this is what this means. This p, the p that I wrote down here, is this expression. Okay, so rather than saying a p of, you can say an expression of x, y, y prime, double, and so on. So that is the order, a differential equation of order n. Now, that is very general. For us, we will do the two cases that we will look in. We will do like first order, and then later on we'll also look at second order. So these are the only two that we will look at. Okay? And in the first order, so how does the first order look like? Well, so that is a function, y prime depends on an expression just involving x and y. Right? Because y prime is first order, then on the right hand side, nothing can be, everything has to be of lesser order, but lesser order just means no derivatives anymore. That's how the second derivative look like. Well, that would be an expression involving x, y, but also y prime. Okay, that's we saw an example here, and here first order. This is an example of this is an example of second order. Here this is the example of first order. Okay, so that's what these differential equations are. And a solution would be, well, it's a function that if you plug in the function for y, so a solution is a function f of x such that if you put y equal to f of x, and of course y prime is then f prime of x, and y double prime is then f double prime of x, etc., and you plug this into the equation, you get an equality. Okay, it satisfies that equation. That's what a solution is. So it's a function that depends on x. Now, there are a couple of things that we have to be careful about. First of all, it might be that this function doesn't exist everywhere. We will see this, that there were cases where that you have to exclude certain points. That's not surprising because we have seen even if, for instance, if you antiderive 1 over x dx, you all say, oh, that's ln x, professor. I know, plus a constant, perhaps, okay? Plus the constant, we'll talk about this a little bit later. But of course, this as a function, this is not defined on 0. The ln of 0 is negative infinity, if you want. Okay? In the limit, you get negative infinity. So this can also happen here, that there are solution functions that are not everywhere defined. And that's perfectly fine. What we're looking for are so-called continuous solutions. But this is the introduction to differential equations. It's not a graduate course. It's not a master's course. So we're not really going to pay attention to what happens if the function is not continuous and problems like that. Although perhaps at the very end we might say something about this. But for now, continuous just means it's an expression that well behaves everywhere, just involving the function that we know, exponentials, derivatives, trig functions, dividing, and so on. But rational functions, we know they are sometimes not defined at a certain point, so we have to look at the domain of the function. But that's not really the whole thing, although this is what we're going to do. We're going to look for solutions. Now, first of all, you can ask, are there solutions? Sure, that's not always obvious, but we'll talk about we'll see in many cases we are guaranteed that these things exist. And then the next thing you can ask is, well, is there only one solution? Now, there you should already know no, that's not true, because we know that when we antiderive, we have a constant of integration. So there are many antiderivatives. Just for this, so this again, what is the corresponding differential equation would be y prime is 1 over x, right? And so this differential equation has many solutions, ln x plus c, okay, for every c. It's not entirely correct what I'm saying, but I'm going to be sweeping all these problems under the carpet, so to speak. X could be negative. What is then? So then people normally write an absolute value there. So then it's defined also for negative x, but still the problem is not defined at 0. So we have to kind of distinguish between the part on the left side of the x-axis from minus infinity to 0, not including 0, and then also on the other side. So this is what we had discussed about functions not always everywhere defined. Okay, and also we have several ones, not just one, but several solutions. And we will see that that's a phenomenon that is very typical for differential equations. There's not just going to be one solution. And in fact, what one can do then, therefore, is sometimes say, okay, if I want to have exactly one solution, I have to put in what is called an initial condition. So if I say, okay, I want a solution to this differential equation such that if x is 1, then y should also be 1. Okay, it doesn't matter what I choose here, right? I say y of 1 is 1. So this is what we call an initial condition. But for instance, another initial condition would be if y is 5, y of 5 should be 100. That's an initial condition. Anything of this sort where we specify a certain value for x and say that should be then the value of that if the input is 5, the output should be 100. That's what we're saying. And then we know that there is a unique solution here. Let's see, if I want this here, so I know that so let me make a little bit of space here and show you how we do this. This is all introduction, right? So this is not really what we're going to do, but just to give you an idea of why things will work. So we know that the general solution is the form ln of x plus c. Let's write the absolute value. And now we say that if I plug in 1, so I plug in 1 here, so y of 1 should be the ln of 1 plus c. I plug in 1 in both sides. Now, the condition is that this should be 1. Okay. Now the ln of 1 is 0. I hope you can easily verify this. So it tells me that from this I see that c is 1. So our solution to this question therefore is y is 1 over x plus 1. Okay, and so we see that there is actually a unique solution. If I impose an initial condition, I get a unique solution. So let me write down this. So initial condition. Let's look a little bit at this word. Initial seems to say, often we think of initial as beginning 0, right? Now, why don't I take 0 here? Because the function is not defined at 0. So initial conditions only make sense at points where the function is defined. And it doesn't have to be initial in the obvious sense of being 0. Well, it's not possible here. It could be anything. But very, very often it will be 0. Okay? Because most cases we will not run into a problem like this, not defined at 0. Okay. So this is of this very simple differential equation here with a simple initial condition, and we saw that it has a unique solution. And that actually is a pattern that is true in general. We will see this is true for first order. If you take a first order differential equation, and special types of it at least, and you have an initial condition, you get an exactly one solution. What about second order? Well, there you need 2 initial conditions, and very typically, so now I'm assuming that my solution is defined at 0. So we would then say y0 initial condition, and we say y0 has to be equal to 5. And what is the next? So I said we need 2 conditions. The next condition you would say, oh, and I find not that ask it at a different point. No, I'm going to ask it at of the derivative. I'm going to require that the derivative at 0 is a given, say, 8. Now this should not surprise you, because, for instance, you have actually solved a second order differential equation in calculus. Let's look at this one. This is the free-falling, the motion of a free-falling object. So here the variable is now t. So sometimes if you want to denote what the variable is, we write t here. And on Earth. The 32 is 32 feet per second square. 32 feet per second square. That is the gravitational constant of Earth in feet per square. Okay, depends a bit on the units, of course, what you use here. And then I'm going to go this very quickly, so please go look up in your book. What you say then is, okay, if I antiderive this, then this is 32t plus constant c. If I antiderive this one more time, that is minus 32t squared over 2 plus ct plus d, where d is another integration constant, and it might be different from the first. And how do we determine these things? Where did they come from? If I'm standing on a building and I jump up and then I fall down, why is there a C and a D there? Right? There's only one possible way for me to move and unfortunately die unless I have a parachute, but then it would be not a free-falling problem anymore. We will talk about what happens when you wear parachutes and so on, how to calculate the movement of somebody in gravitational field. So where does this come from? Well, these were the initial conditions. I said I was standing on a building, so this would be at time 0, when I start my jump, this would be the value here. If I plug in 0 now, y of 0, these two terms disappear, right? Because there's a t there. So that is 0. So this d is actually the initial position I have. Say I'm standing somewhere in a building of, let's say, 500 feet high. Well, okay, that is my d here. And what is this c then? Well, look at here. Here you can see if I plug in 0 here in this equation, then the first term again disappears and get c. So c is the initial velocity, because I said I jump up. So there is an initial velocity here, that part of my jump. So determining my initial velocity and my initial position determines the whole thing. And so there's a unique solution. There's only one way I can fall. And it's always the same. Each time I do this, presuming that I survive, I end up doing exactly the same fall at the exact same time measuring. This is where I'm now ignoring wind and resistance and anything of that nature, right? You know, this is just an ideal solution. So here we see that two conditions, initial conditions, and these two conditions are very special type. They are the initial value of the function and the initial value of the derivative of the function. Okay? Determine completely the function, and that's again what happens in second order and in your higher order, but we won't talk about this. Okay, so the next thing now I want to talk to you about is how does this look like? How can we? So far everything is very abstract and I'm talking about solutions and I'm solving them, but can we always do this? No, so what then? So how to visualize this? We're not going to focus on that, but I just want you to see at least that you can do that. Okay? So suppose, let's say I want to, yes. So the question is how to visualize. But at the same time, I also say apply. And how can we apply this? Okay. Now the visualization is not, we cannot do everything. So the visualization, I'll give an application that can work. But I want to do both at the same time so that you see a little bit why are we doing this and what do we see when we do this. Okay. All right, so the application I'm going to give you is a little bit, is about, so the application is population growth. Oh, you say, oh, Professor, I have heard about this. We've seen this, I remember this. Population growth is exponential growth, and then That's when the base is positive, right? And if the base is bigger than 1, and if the base is for the exponential is smaller than 1, you get actually exponential decay. Okay, population growth, right? And so, but where does this come from? Well, the idea, so here now P is going to be the population, the number of people or members of a society. This could be the number of coronaviruses on Earth, for instance, that is a population, right? Or the number of bacteria in a petri dish. It could also be the number of rabbits that live on a meadow, or many different models can be viewed as this. And what we kind of all know is that, okay, take the example of rabbits, the more rabbits you have, the more little rabbit babies will come, right? And kind of you need like a pair of rabbits to produce one offspring. Well, in bred rabbits, it's very often 4 or 5, okay? So what does that mean is, now remember derivative, and this is, so P is the population, T is time here, because we're going to measure everything. The question is, how does population change with time, okay? So remember that one important for us, for differential equations, is extremely important interpretation of derivative, of the derivative of function, is the rate of growth. The rate at which a function grows or goes down, declines, right? The positive derivative means increasing function, means positive growth. Of course, negative derivative means negative slope of the tangent line, means decline. Okay, so what is that? What I just said was, okay, the more rabbits you had, the more little babies will come. And it's kind of proportional. What does that mean? Proportional means that the rate of change is proportional to the function itself. So A is a proportional constant. Proportional, that's not so important. What it is a constant. In other words, it doesn't change with time, at least in the simple model that we're first going to discuss. So for instance, population growth is very often around 2% or something like that, so A is 0.02, sorry. So for instance, example given, A could be 0.02, 2%, okay? All right, so if we solve this equation, and that is not so hard, and I'm going to actually do this because we will, later on you will see in how we solve these differential equations, and it's very simple. It's a trick. I'm going to divide this here by P, and then this is A. Now what is this here? This is a quotient with the derivative on top and the function on the bottom. And this is what we used in logarithmic differentiation. If we derive this, so then we get ln of P. So what I'm saying is that the derivative of ln of P is exactly that thing. So ln of P derivative is A, right? So let me repeat what I'm saying. This is equal to that. That's a simple rule of, so the derivative here, of course, is with respect to t, right? If I take the derivative of this function, chain rule, again, a very important thing to review in calculus, take the derivative of this function, you get this. So what we see here, the derivative of this function is a. That means we know what does it mean for a function to have a constant derivative. It means that the function itself and the derivative of this function, so ln of p. So we take the integral of both sides, if you want. And the derivative of both sides, that would be at plus a constant c. So c is again a constant. So this is how the solution look like. Now, this is ln of p. We would like to know p itself, the population itself. Okay, so that's the ln. How do you get rid of an ln? By cancelling it with its inverse, which is exponentiation. So I'm going to take e of both sides. E of both sides. So e of ln p, that is just p. And then here we get e of at plus c. And for simplicity, I'm going to separate this a little bit. The product, the sum of exponents is the same as this thing here. Okay. So what is this here? This is just a constant. C was a constant, so EC is a constant. So I'm going to rename the constant. That is something we often do because there's no... if this is a constant, it doesn't matter how I write it. So I'm going to write, so rename this as, let's say, D. EAT. So D is a constant. D is actually e to the power c, but it doesn't matter. Okay, now remember, A is a given constant. So we have to be a bit careful here with the words constant, right? A constant means, at some points we know what a constant is, like in this case, A, and some points like here, the D, we don't know yet what it is. Okay, so some constants are known, others have to still be determined. Sometimes one like to call this then a parameter. So instead of this, I'm going to call T a parameter. So parameter is, let's think of it as a fancy word for a constant that still has to be specified. So that's what a parameter is. It's something that it's actually constant, doesn't depend on t, but we don't know yet the value of it, or we're not interested in the value of it. We leave it as is. Okay, but in case, remember what we said, there is this is an example. You might say, Professor, I don't see it. Why is it an example? Well, I used p, but if I would write it with y's, it would be just this one, right? And hopefully now you see it's a differential equation of this form here. P is just the polynomial, is just a times y. That's just p here. Okay, so it is the differential equation, but I use p because population is more, p of population is more telling. And then we said, okay, if you have a differential equation of first order, it's a first order, then you have to give an initial condition to guarantee a unique solution. So let's say, okay, at time 0 we have a certain amount, and this is very often we need formulas, and we like to use formulas in general. So we call the initial condition p subscript 0. Of course we have a concrete number in mind. As we took a to be 0.2%, we could perhaps think of p0 to be, let's say, for simplicity, 1,000. Okay. So how do we determine now this d here? So we have this equation. Well, it's always you plug in the values, right? So remember, in our case, so the case that we're doing here, p0 was 1,000 and a was 0.02. So what would give me, so let's plug it in, p of 0, that is the 1,000, that is that p subscript 0, that was equal to d, which we don't know yet, e to the power a 0.2 times t. But t is 0, so that's like, oh, that the 0.2 doesn't matter here, so e to the 0, that is just d. D is just the initial population. So the formula therefore is p is equal to p0, remember that's the initial population. I'm going to write down the general formula now, EAT. And A and P0 are numbers that depend on the particular population that you're studying, be it rabbits, be it the world population, be it bacteria in a petri dish, or so on. Okay. Now, a very important thing that one often has to do when one studies these things in real life is, how does this function behave? And in particular, what we're wondering about is what happens if time increases. And so what is the limit if t goes to infinity? Well, first of all, you should notice that if a is bigger than 0, then this increases. This is an increasing function. And this is what we call exponential growth. That's where exponential growth comes from. It's from this solving this simple idea that a population grows as fast as the number of people, or proportional to the number of people, of members that it has. That is expressed by this differential equation. Then we solve this differential equation and we see that we get an exponential, and that is what we call exponential growth. Now, there is a thing, if a is positive, then it's increasing. If a is negative, then it's decreasing. You say, how can it be negative, Professor? Well, for instance, what is the population growth in real life, say, for the world? Well, the growth of our population depends on two things: how many people die and how many people get born, right? So there's a rate of dying and there's a rate of getting born. And so what is the total, what is this A here? Well, it's the rate at which our population new members get born, minus the rate at which the death rate of the population. So birth rate minus death rate, that's what this A is. So this A represents birth rate minus death rate. And we assume that this for a population is a constant, right? That this doesn't change over time, that we always have, no matter how many people we have, the birth rate is the same and the death rate is the same. Kind of what we see in our society, right? Most couples have, let's say, 2 children, okay? And most people live about 75 years. So the death rate is kind of always the same, birth rate is kind of always the same. These things do change over time, by the way. In earlier times, the death rate was, of course, much worse, but the birth rate was much higher because people would have many more children. So that somehow compensated each other, but okay, so it could be negative, and you have declining populations, that too many people die while there are not enough people born into the community. So what is the limit here? Well, the limit therefore is, if I plug in infinity, right? Plug in infinity here. If this is positive, then this goes to positive infinity. So the limit for t of this function is positive infinity if a is bigger than 0. What is the limit if this is negative? Then this goes to negative infinity. E to the negative infinity, that is 1 over e to the infinity, that is 1 over infinity is 0. So if you have if the birth rate is higher than the death rate, you're going to eventually end up with infinitely many people. That means the population will can get as big as you can think of as time expires, which is of course awful. Remember, there's only so much space on Earth, so if we're going to go infinitely many people, or 700 quadrillion people, they're not all going to fit on Earth, okay, after some time. If on the other hand, fertility is down, so that the birth rate is less than the death rate, well, then eventually we will end up being with nobody left. Okay. Now, is this a realistic model? No, because that's not what happened, right? If you would put this model in and you would apply it, say, with 10,000 years ago, when after the first ice age, you might say, okay, nothing really dramatic happened to human beings at the time. There was no major calamities anymore on a world scale. Of course, there were small calamities, but on a large scale. So from 10,000 years ago, this process should have been going on. And if you put in the numbers, you might probably get populations that are no longer make sense anymore, way too big. And perhaps when we're dealing with Earth, we're still within the limits, but we're dealing with, for instance, rabbits. Take a big cage and you put in 50 rabbits there. Okay, according to these models, after, let's say, a couple of months, there should be 5,000 rabbits in that cage, which is impossible. So this is an unrealistic model. So many people have proposed models, and the Verhulst model, and Verhulst is Verhulst, I should say it in my own language because he's Belgian, as I am. He came up with the following model. Says, okay, we have to take into account that once population gets bigger, there's competition about resources and space, and so the population it's not going to be proportional anymore. But the model that he proposes, sorry, I have to look this up because, of course, although I'm Belgian, don't know these formulas. Okay, AP1 minus alpha P. So where A and alpha are again constants that depend on the particular type of population you look at. So they are concrete. They could be concretely calculated. Okay. So this is a totally different thing. First of all, let's write this with y's, then we see perhaps better. AY minus 1 alpha y. And of course you could expand here and you see this would be a quadratic in y. Is that therefore a second order? No. That's the degree is not what order determines. It's the first derivative, so it's still a first order, but okay, now the expression that you get is something quadratic in y. Notice that there is no t here, the variable t. That could also happen, but it doesn't. In this model, there is no t. So a and alpha are just constants, so they don't depend on t. So this is the model that is proposed, and we can actually write down a solution. So come back later to see how this is done. But I'm going to write down the solution. The solution is of the form P0, the initial population. Remember, that's what it stands for. And so it is a little bit of a 1 minus alpha P0 e to the minus at. It looks different, right? It looks more complicated than our original formula that we had here. This is the original one. So this is the naive model, if you want. This is the Verhulst model. And this is often considered as a good first approximation. Okay, so let's look at these limits here. What is the limit? Let's do this in our head, hopefully. And let's for simplicity assume that A is positive. We're dealing with positive growth here. So if I plug infinity here, this goes to negative infinity. Remember, e to the negative infinity was 0. Okay. So I'm assuming here A is bigger than 0. So this means that so now we take the limit for t going to infinity. Then this whole thing becomes 0. So what I get is P0 over alpha P0. Oh, the P0s cancel out, and I get 1 over alpha. This is strange, right? First of all, it says that if you wait long enough, then the population is basically a constant. So the population is going to this ideal number. This what we call equilibrium state, a balance. There's just this many people. There's just enough people die, and just enough people get born so that the population remains constant. But this is only after a long time. Okay, and this is what you kind of would like, right? And this is, for instance, what you want with coronavirus. You want the virus to eventually be a constant number that we can keep under tap, so to speak, that it doesn't blow up, that it keep that the epidemic is that would be the end of the epidemic. Okay. All right. So so this is one thing. The other thing is, but even stranger, is that it actually doesn't depend on how many people you started off. Okay? This doesn't depend on P0. The original function depends on P0. Yeah. If you start with 1 million people, sure, this model is gonna give you values that depend on this 1 million people. But after a while, or a long while perhaps, t going to infinity could be t for 1 million years, which is of course something that doesn't apply to us, but depends a little bit on the situation. In fact, very often it's actually not that long. We see that this would lead to a certain constant population, regardless of how many you started. Well, I guess you have to start with 2, right? You understand why, right? And it has to be of different gender, otherwise you're still a bit of a problem. But eventually, this is what happens. Okay, so now last thing is, can we see somehow this? How do we see this? I said application, but I also want to talk about visualization. And for first order, and this is something I'm going to do very quickly, we can do this. So I'm going to, of course, in here, okay, sorry. I'm jumping a little bit. Let me go back to what I'm trying to say. Here we have a formula. Let me get rid of this red here. Okay, so this is now back to no longer the limit, to the actual function here, the actual solution. We have a function and we can plot this function, and this is so-called the logistic function. It bears this name because it is, this is called the logistic equation. Don't ask me exactly why, but and we can plot this function, and we see the graph of this function, and we have this. What does this mean? That in the limit, this went to 1 over alpha, right? This means that this is a horizontal asymptote. Think a bit about this, but if you go back, look at what horizontal asymptote is, that's exactly what this means. That the limit at infinity. Okay, so these functions all look a bit like this. There are different functions depending on different values of alpha and a, right? Alpha, different values of P0. But they all look a bit like that. Okay, so here the visualization is rather simple. But suppose now I would like to visualize this thing here. Let's do -1. have to make sure that I get the right thing here. No, minus x over y. This is a differential equation. You agree with me? Okay. This you think this might be a little bit harder than I can deal with. Yeah, okay. We will see how we can solve these things later. But I'm going to show you the solution already. And this is something that works for any first order equation. So this is called the, I'll follow the concept of the book, direction field. They call it direction field. Of a first order differential equation, DE. What is the idea? Well, I want to plot this, and what I'm doing is the following. So I'm going to take a grid, paper, let's take a small grid here, like take this grid. So you see a grid here, let's take this grid for instance, okay? And for each point in my grid, well, except for, I have to be careful, I cannot do y equals 0 here, right? I cannot plug in y equals 0. So this is my x-axis, my y-axis. So in this case, I should perhaps, let me get rid of these two dots here that I made. Okay. So, this is the y-axis, and this is the x-axis. Now, I'm going to use all the dots. Let's stay away from 0, because in 0 we get this whole thing. So I'm going to look at all these dots here. Okay, let's restrict ourselves to 5 by 5 here. There's no need to do this, but I'm just for purposes. Okay. So let's look at these 25 points that I've marked here. And each of these points has an x and y coordinate, so I can plug that in here, and I get a value, and that value would be the slope of this function at that point, right? Because that's y prime is. Y prime is the slope. So what I'm going to do is, I'm going to put, suppose we are calculating this for this point. I'm not going to do it concretely. I'll show you the picture later. But so in general, you have y prime depends on x and y. Remember, this is our any first order differential equation looks like. So you take the x and y coordinate of this point. So let's do this we're concentrating on this point. This would be here, for instance, 2, 2, say. You plug this in, so you calculate P2 of 2, and that will be the slope of the function at that point. So I put, let's say, suppose that P of P22 is, let's say, 2. Okay, this means that it has a slope, what is 2? Rise over run, right? So when you go 1 to the left, you go 2 up. So this would be a slope of this. This would be, I put a little vector, a little arrow that points in this direction with slope 2. Okay? And I do this for every point. Now, in order for the picture to be a little bit legible, I'm going to make the vector a little bit smaller than that. So, okay, so I'm going to do the same thing, but the size of the vector doesn't matter. It's the direction. We only are interested in direction. So I do this for this, I do this for here, I do this for here, I do this for here. So perhaps this is the pattern that emerges, and I get something this and this and this. So you get all these little arrows, but these little arrows, what you're not going to have is something like that, and then this, and then this. They are not just turning wildly. No, there is going to be some. You'll see that if I, like for instance, suppose we have something like this here. So I'm taking this point, and this vector tells me, okay, go to this point, and this vector tells you go to this point. So I can kind of connect all the little arrows and get a line. And this curve that I get to see here is the solution. Will be a solution, because that's if I start from this point. Now, if I start from this point, this tells me totally different thing. I have to go this way, I have to go this way, I have to go this way. So perhaps then if you start from this point, the solution might look something like that. Okay, let me do this in practice. So let's go. I'm using a online web app for this. You could find this many places. So I'll put a link on the web page so that you can go to this, or you can find a similar thing like that. This is not a very fancy one. It's this one. It says here, and for a more sophisticated one, go to MATLAB Plotter, but that link is dead. So what is this does? Well, okay, so here, sorry, I cannot point in on this thing here. So we have here, in that field, you fill in the equation of your function that you want. In this particular case, this was sine y cosine y, sine y times cosine t. Yeah, the instructions are that you should use the variables are y and t. Okay, and then you put in the number of arrows. This is the last of the columns that you see here. Number of arrows here, so 20. Okay, you put the 20 or many you want, and then you say graph direction field, and you see these little arrows that I was talking about. Okay, instead of having them centered at the points, they are now centered in the middle of the squares. But that really doesn't matter. What you see is that you see kind of lines emerging. If you follow this vector, you kind yes, this is very bad. I can. There's no way for me to, because I'm on Safari now, so I cannot point on you. Oh, I actually did it for me. Huh. Okay, yeah, right, see? Oh, okay, that's nice. I didn't realize you could do that. So if I do it here, see, if you say start from this vector and it says, okay, then follow this line, follow this line, follow this, follows up, follow up, and down and up. You see the line that it creates is exactly the what it expects. This is a curve. This curve that you see is the solution of this differential equation. Now, we don't have the equation of this curve, but we have graphical visualization of this curve. Now, let's do this for the one that we were interested in. Oh, this has even a pencil here, but I don't want to do this. I want my keyboard, okay? So, so there was minus, yeah, this is from iPads as the least good thing to use for this kind of things, but okay. Divided by, so if you do this with a computer instead of an iPad or an iPhone, okay, that is what I want. So let's graph the direction field. Oh, okay. Yeah, okay, that's, oh no, it was, what was the equation that I said it would do? I think I do the Rengo equation, right, it's the other way around. Just, this looks a little bit like hyperbolas, right? Sorry, but I did the wrong one. It was minus t over y, right? You got that? Yeah, sorry, I don't want to jump back, but that's the one I should have done. That's the one I said I was going to do, minus t over y, okay. Graph direction field. Huh. Oh, they kind of circles around. So if you want to see a little bit more, let's put a little bit more circles there, more arrows there. Let's put a 100 of these arrows. Sorry, no, I do here. 0, 0. See, now I put so many that it kind of, the picture is a bit too dense. I cannot really see what happens here. So 100 was perhaps a little bit too much. Let's do perhaps therefore 40. So you have to play a little bit to oh, that was an O instead of a 0, so that doesn't know what to do with that. Okay. And now you see really clear the circles, right? So let me again try here. If I put this, you see, hello, yeah, see? He gives the circle. Now he gives only one part of the circle, but he should also give the other part of the circle. And this is also the point that I want to make. So the solution is the full circle. And with radius, whatever radius, you see every circle with any radius appears here as long as it's centered at the origin. So the solution of this particular differential equation, therefore, is any circle with center in the centered at the origin, no matter what its radius is. Okay, and that's exactly determining the radius makes it then a unique solution. That's the initial condition will give you the radius and then gives you the unique solution. But what I want to point out is that this is not really the red curve that I have is not really a function of a t, because it's not a graph of a function. It's a graph of two functions. And it is exactly, let's do it another one. This is the bottom part of the graph, and this is the top part of the graph. So the graph consists of two parts, but the whole curve is actually a solution. So sometimes we talk about a solution curve. That means a curve like a circle like this, or could be more complicated like that. I'll put another thing here. just for the fun of it, let's make this a little bit different. I'm just going to plug in something. I don't know if you know what this will give me. Sorry. Let's do here y plus t. I don't know why, but I want this y plus. Where is my plus? Hello. Here plus t, and then I have to close the bracket and parentheses. Okay, so direction field. Okay, so it looks a little bit different, right? So let's take a line here. You see it kind of looks like a little bit of like, I don't know. We'll do it here. Now what you also see is this white line here where just nothing seems to happen, and it's exactly because that's the point. These points are the points where the denominator is undefined, and that's why these points do not exist. So that's what we had talked about. These curves sometimes don't they have discontinuities in the sense they are not defined at certain points. Okay, so this is something you can play with. I'll allow you, please try out a little bit. And you can use this later also when we do first order differential equations to actually visualize it. At least then you see at least what can you expect here. What is there going to happen? But this kind of already tells you that you can always solve this, right? Because you have all these arrows and you just have to follow the arrows. So solutions do always exist, right? And what's the initial condition? Well, initial condition would be the value at time t equals 0, right? So why would this lie? This would, so if let's say I want to find a solution with the initial condition y of 0 equals 3. Well, the y-axis is the vertical axis, and 3, this is 3, right? So I put the 3 here, look, and this gives me the solution that has exactly the value 3, and this is exactly 1. So you see here that graphically you see that all that I was saying before is actually true and works. Okay, so that's all I'm going to say for the introduction, and then we will go to the special cases in next videos.